department had a meeting and we were trying to figure out what our mission statement was. And nobody laughed when somebody said to save the world. We really feel this compelling need to address some of these problems we have. We can't just hide our heads in the sand and hope that climate change is going to go away. Hi, I'm Professor Brian Haus. I'm with the University of Miami's Rosenstiel School. I'm in the Ocean Sciences Department. My background is in coastal engineering. I got my degree from the University of Michigan many moons ago. And I am here doing research on air-sea interaction and waves. And I'm here in the SUSTAIN facility, unique in the world facility to do measurements of the air-sea interaction in extreme conditions. The facility is pretty large scale for a wind wave laboratory. So these two labs allow us to study a wide range of the phenomena that are occurring. And we can blow on the big facility a wind speed of a real Category 5 wind inside the tank without doing any scaling. That's the highest wind speed of any wind over water facility in the world. And its width allows us to generate directional waves with that wind, which is very important as well. Another aspect is the seawater that we can put in it. Seawater can be very important for this problem because seawater spray, the water that comes off in a really intense wind, is different than freshwater spray. And not that many labs are right on the ocean where they can suck in fresh seawater and use the measurements there. And the fact that it's out of acrylic allows us to visualize really well what we see. Hurricanes, first of all, we know they don't form over Kansas. So hurricanes are a phenomenon that occurs over ocean waters. And they occur in the summer because they occur over warm ocean waters. So the thing that happens as an atmospheric system moves over the ocean is that this triggers this motion of the hurricane. But the hurricane has to get its energy, what powers a storm, from the ocean. So it's drawing heat off of the ocean and spinning over the ocean. And these processes, these small-scale processes that happen at where the atmosphere and ocean meet, are very important for determining how a hurricane is going to develop and how it's going to intensify. And there's a lot of unknowns about how those processes happen because it's really difficult to measure them in a real hurricane. So here in the SUSTAIN lab, we can work to understand these fundamental processes of how heat is transferred to power a storm and the friction the ocean exerts on the storm as it spins. And these things are involved in the process was known as rapid intensification, which causes a storm to go from a Category 1 to a Category 4 in 24 hours. And we've seen a lot more of that happening lately. And it's really important for safety of coastal communities. Because here in South Florida, if we think a Category 1 storm is coming and it turns out to be a Category 3 or 4, it's a lot different. You want to know that's going to happen as soon as possible, because you can't react real quickly if it comes as a surprise. Well, over the last few decades, as computers have gotten more and more powerful and we've been getting able to run global weather models with these better resolution, the ability to say where a storm is going has been getting better and better over time. But the other component of this is how strong it's going to be. What is the intensity of the storm? Because it's not enough just to know a storm is coming. You'd really like to know how strong it is to know which buildings, which people need to be evacuated, what's at risk. And that part of it is not as well understood and has not been getting a lot better over time. And so the question is, why is that? And we think there's a lot of the processes related to the coupling of the atmosphere and ocean, the exchanges of heat and momentum between the atmosphere and ocean, the friction of the ocean and the heat that goes up, as well as details of things that happen in the storm. And in the laboratory here, we can start to shed light on some of these things that may be controlling intensity, because we can make detailed small-scale measurements in these really intense conditions and then see how that, if you change the assumptions about these things, they can change what the model is predicting for intensity. So one of the things that a lot of people don't understand when you hear the storm surge is going to be 6 feet or a prediction of what the storm is 2 feet, is that the surge itself The initial water comes in pretty fast, but in addition to that, it's not just that the elevation suddenly came up. That is like a truck hitting a building. Think about all the heaviness of a big volume of water hitting a structure. It also has, in a hurricane, landfalling hurricane, it's got waves riding on it. It's got the wind pushing at really high speeds. And we have, some formulations, although there's not a lot of data, and we're working to correct that on the wind impacts alone, the wave impacts alone, and then you can look at the surge. But when you consider all those things that could be actually happening at the same time, those are really not well understood, and that's what we're trying to improve in this facility by running scaled model testing. Like, we can't put a whole building or a bridge in here, but we can put a scaled model of a building or bridge and understand how the wind and the waves and the surge interact with that structure. And if we get enough information at the laboratory scale, we can then use models to extrapolate that information up to full scale in some cases. So, among the things that we're doing in the laboratory, in addition to understanding the impacts on structures that exist, is say, okay, well, what can we learn about these impacts, these forces that are on the structures, and how can we design better to reduce the amount of impact on a seawall or a structure if we use different designs? And how can we do this in a way that's compatible with nature as opposed to fighting nature? And so we're looking at these called nature-based solutions, or hybrid solutions, which is a hybrid engineered nature-based solution. So we're involved in studies for deploying new designs with these hexagonal sea hive structures that dissipate the energy and take some of that away before it bounces back. Or in a case of a reef, you can maybe get away with less concrete, so it's a more sustainable solution in that sense as well. The issue of climate change underlies a lot of the research that we're doing because it's changing some of the fundamental processes that occur in the ocean. So for hurricanes, we've already seen that hurricanes are getting more intense, they're moving slower, they're wetter. And these three things together all are combined to create more deadly and more dangerous storms. So you look at things like Hurricane Harvey, which have, events like that have happened in the past, but are we going to get more of these super wet, slow-moving storms that, really flood out urban areas and things like that? These are the kinds of questions that we have to be concerned about as temperatures warm in the ocean, and these can have far-reaching impacts. Over the years, as these problems we have just gotten worse and worse, and I have, I'm invested in South Florida, I have a house here, I have a family here, you start to feel this responsibility to your community and to the world, and I think that's grown over the time. And as these problems have gotten more severe across so many different ways, algal blooms, sea level rise, direct impacts, things like this, hurricanes, it just really, you really feel like, it's exciting work, but it's really important. So it's definitely invokes some passion. You can create a career in this field now out of a lot of different paths and follow your passions. I guess the neat thing what doing is science, and I'll advocate for doing scientific research, is we never do the same thing twice. We may run an experiment 3 or 4 times to get some statistical certainty, but we never, the next week we're trying to figure out how to do it better. And so it's very creative too, and I think we need to think of them more in that way, that we're trying to create new knowledge about our world.